Fundamentals of HVACR, Chapter 11, Types of Refrigeration Systems. Objectives include: explain the fundamental principles of the compression refrigeration cycle, describe the relationships within the refrigeration cycle, describe how heat flows in the refrigeration cycle, discuss the difference between the compression refrigeration cycle and the absorption refrigeration cycle. Explain the fundamental principles of evaporative cooling, and explain the basic operation of thermoelectric refrigeration. Air conditioning systems cool people. Commercial refrigeration systems are chiefly concerned with cooling products, and industrial process refrigeration is used to cool equipment and machinery in large industrial manufacturing plants. Most machines that cool or refrigerate something use the same mechanical refrigeration cycle. This cycle depends upon a few basic physical principles. Cold is not a substance or an energy form. It is a lack of heat. Refrigeration machines do not pump cold in, they pump heat out. Heat travels from hot to cold. Liquids absorb large amounts of heat when they boil off to a gas. Gases give off large amounts of heat when they condense to a liquid. The temperature at which a liquid boils is controlled by its pressure. To understand the refrigeration cycle, you must understand the relationship between physical properties of refrigerant. For example, the relationship between pressure and temperature. Refrigerant pressures and temperatures are linked. If a refrigerant is a high pressure, it is also a high temperature. If it is a low pressure, it is also a low temperature. Gas always has a relatively high heat content. Even a cold gas has a high heat content. For example, saturated R-410A gas has an enthalpy, that is heat content, of 123 BTUs per pound at 100 degrees Fahrenheit. Even at 30 degrees Fahrenheit, it still has an enthalpy of 121 BTUs per pound, nearly the same even though it is now a cold gas. The refrigerant state is far more important than the temperature in determining the heat content. Liquid always has a relatively low heat content. Even a warm liquid has relatively low heat. For example, saturated R-410A liquid has an enthalpy, that is heat content, of 25 BTUs per pound at 30 degrees Fahrenheit. At 100 degrees Fahrenheit, it still has an enthalpy of only 52 BTUs per pound, even though it is now a warm liquid. The refrigerant state is far more important than the temperature in determining heat content. Gas always has a higher heat content than a liquid of the same substance. Comparing the last two slides, we see that an R-410A saturated gas at 30 degrees Fahrenheit has more than twice as much heat as a 100 degree Fahrenheit liquid. The heat content is determined mostly by the refrigerant state. Refrigerant will be found in the system in one of three conditions: superheated, that is all gas; saturated, a gas-liquid mixture; and subcooled, which is all liquid. Superheated gas is heated above the saturation point, that is, the boiling point. Superheated gas is all gas with no liquid. Since the saturation point changes with pressure, it is possible to have a superheated gas that is a low temperature if the gas is at a low pressure. For example, R-410A gas at 118 psig and 50 degrees Fahrenheit is superheated because it has a higher temperature than its saturation temperature of 40 degrees. A saturated mixture is a mix of liquid and gas at the saturation point. The refrigerant is saturated any place in the system where the refrigerant changes state. Adding heat to a saturated mixture causes some of the liquid to boil to a gas without changing in temperature. Removing heat from a saturated mixture causes some of the gas to condense to liquid without changing temperature. An R410A liquid gas mixture at 118 psi and 40 degrees Fahrenheit is saturated. The refrigerant is saturated any place in the system where the refrigerant changes state. A subcooled liquid is cooled below the saturation point, or boiling point. Subcooled liquid is all liquid with no gas. Since the saturation point changes with pressure, it is possible to have a subcooled liquid that is at a high temperature if the liquid is also at a high pressure. R410A liquid at 318 psi and 90 degrees Fahrenheit is subcooled. This is because it is at a lower temperature than its saturation temperature of 100 degrees. The best way to understand the refrigeration cycle is to understand the relationship between the components. A mechanical refrigeration system has a high pressure side and a low pressure side. The compressor and expansion device are the dividing points between the high and low pressure sides. The compressor raises the refrigerant pressure to create the high pressure side. The condenser is on the high pressure side of the system. The refrigerant expansion device creates the low pressure side by dropping the refrigerant pressure and temperature. The evaporator is on the low pressure side of the system. Each of the four main components of the basic refrigeration cycle has an opposite. The compressor and expansion device are opposites. They are the dividing points between the high side and the low side of the system. This chart shows how the compressor and expansion device operate almost exactly backwards from each other. The compressor raises the pressure and temperature of the gas by reducing its volume. The expansion device lowers the pressure and temperature of the liquid by increasing its volume. The evaporator and condenser are opposites. They are the components responsible for moving heat into and out of the refrigeration system. This chart shows how the evaporator and condenser operate oppositely in most every respect. The evaporator absorbs heat by boiling a liquid to a gas at a low pressure and temperature. The condenser releases heat by condensing a gas to a liquid at a high pressure and temperature. The evaporator absorbs heat into the refrigerant, and the compressor adds heat to the refrigerant through the heat of compression. The condenser must expel both the heat absorbed in the evaporator and the heat of compression. Heat added in the evaporator plus the heat of compression equals the heat rejected in the condenser. Absorption systems use heat and the absorption process to move refrigerant instead of a compressor. The absorption process takes advantage of the fact that some chemicals have an affinity for other chemicals. Water will absorb half its weight in ammonia. Like the compression system, absorption systems have a condenser, expansion device, and evaporator. The transfer of heat is essentially the same in the absorption system as in the traditional mechanical compression cycle. Heat is absorbed in the evaporator under a low pressure and rejected in the condenser under a high pressure. However, the absorption system replaces the compressor with a generator to create the high side pressure and an absorber to create the low side pressure and a solution pump to move the solution from the low side to the high side. The absorption system really has two cycles, a refrigerant cycle and an absorbent cycle. Both the refrigerant and absorbent cycles have a high pressure side and a low pressure side. The high and low pressure sides are separated by the refrigerant expansion device, the solution restrictor, and the solution pump. Boiling the refrigerant in the generator creates the high side pressure. The solution pump moves the refrigerant and absorbent from the low pressure side to the high pressure side. The low pressure side is created by the absorber. The absorption process replaces the suction stroke of the compressor. Refrigerant from the evaporator is absorbed into the solution in the absorber, creating a low pressure in the evaporator. An absorption system really has two cycles, the refrigerant cycle and the absorption cycle. The refrigerant cycle includes the generator, condenser, expansion device, evaporator, absorber, and solution pump. The absorption cycle includes the generator, solution restrictor, absorber, and solution pump. Note that the generator, absorber, and solution pump are part of both cycles. The solution restrictor and its piping are only involved in the absorbent cycle. In this slide, we see both the refrigerant cycle and the absorbent cycle working at the same time together. The generator holds a solution of water, the absorbent, and ammonia, the refrigerant. Heat is applied to the generator to boil the ammonia out of the water and create a high pressure. The high-pressure ammonia gas travels to the condenser where it is condensed to a liquid, giving off heat. The liquid ammonia pressure is reduced at the expansion device and fed to the evaporator at a low pressure and temperature. In the evaporator, the ammonia absorbs heat as it evaporates. The ammonia vapor is drawn into the absorber by a water spray. The water absorbs the ammonia, creating a low pressure in the evaporator. A solution pump returns the low-pressure ammonia-water solution to the generator. The ammonia and water are separated in the generator. The ammonia boils out of the water, leaving mostly water in the bottom. The high pressure of the generator forces the water at the bottom of the generator to travel through the solution restrictor where its pressure is reduced. This low-pressure water is sprayed out in the absorber to absorb ammonia vapor. When the ammonia vapor is absorbed into the water, it condenses to a liquid, giving off heat. This heat is called the heat of absorption. The heat balance of the combined refrigeration and absorbent cycles in an absorption system is the heat applied to the generator plus the heat absorbed by the evaporator equals the heat rejected by the condenser plus the heat rejected by the absorber. Evaporative cooling reduces air temperature by evaporating water. Air that has been cooled through direct evaporative cooling still has the same amount of heat, but its temperature is lower and its humidity is higher. Evaporative coolers can drop the air temperature by as much as 20 degrees Fahrenheit if the entering air is dry. This chart shows the change in the air in an evaporative cooling system. The air goes in at 95 degrees dry bulb and comes out at 75 degrees dry bulb. Notice the wet bulb does not really change. The relative humidity actually goes up, as do the grains of moisture. The enthalpy stays the same. There is no real heat change in evaporative cooling. What we get is a sensible change. In other words, we're reducing the air's temperature. This works quite well in dry climates. It's not necessarily a good trade-off in wet or muggy climates. Parts for a direct evaporative cooler include a sump to collect water, a pump to move the water, a float to control the water into the sump, media for the water to trickle over, and a blower to move air across it. The pump pumps the water from the sump at the bottom to the top of the media where it runs down the media. The blower moves air outside across the media into the house. Water evaporates from wetted media, reducing the temperature of the air. A float controls the water level in the sump by allowing makeup water to fill the sump when the water level drops. Direct evaporative coolers are constantly replacing the air in the house with air from outside that has been cooled by evaporation. For this system to operate correctly, air in the house must be allowed to escape. This is normally done by opening windows. Thermoelectric cooling works by sending DC current through a thermocouple. A thermocouple is made up of two different metals joined at two places. When current flows through it, one junction gets hot and the other becomes cold. The electrons are transferring the heat from the cold junction to the hot junction. This phenomenon is known as the Peltier effect. Today's thermoelectric modules typically use semiconductors sandwiched between two heat sinks to produce a unit capable of moving heat. Although thermoelectric cooling is not very efficient, it can provide a small, lightweight cooling system for areas that would be difficult to cool with a traditional refrigeration system. Thermoelectric cooling has been applied to electronic systems, spaceships, and picnic coolers. The purpose of a refrigeration system is to move heat from where it is not wanted to where it is unobjectionable. There are several kinds of cooling systems, including absorption, evaporative, thermoelectric, and mechanical compression. Other cooling mechanisms include evaporative coolers, which cool the air by evaporating water, the absorption cycle, which uses heat and an absorbent fluid to create the needed system pressure difference, and thermoelectric cooling, which transfers heat using electric current and the Peltier effect.